All right, hello, and welcome to Mr. Linford's live stream for the afternoon session on March 25th. What we're going to do in today's discussion, similar to what we did in first hour, I'm going to go through what you should have gone over yesterday, section 10.8 day 1, and then a couple of the problems from section 10.8 day 2. If you have any questions or things you are curious about me going over or that you want to review, even stuff from part 1 of Unit 5, feel free to let me know. Let me know in the live chat here, and I will make sure to cover those topics for you. Right now, I figured we'd start with some of the exit ticket problems from yesterday. In particular, how to go about simplifying something that has a negative radicand to it. So, with complex numbers, we are now able to simplify negative radicands, expressions that have negatives on the inside of the radical. So we should have seen that really this is not really that difficult of a problem to do, right? It's pretty standard. It's something that we've actually covered before. We're just adding one extra step to it. So when we go and simplify this, we want to separate out the radical just like we did in the previous section. But this time, we have to contend with what is the square root of negative 1. So I'm going to start breaking this down like normal. 98, I know, breaks down into 2 and 49. So before I keep going through all the prime factors, I know I have a perfect square right there. So I'm going to break this up into the square root of negative 1, the square root of 49, the square root of 2, and then x cubed we can break up into the square root of x squared, and the square root of x to the first, and then the square root of y squared. So I'm going to switch up colors here, and I'm going to break down each of these and try to show try to show how everything gets broken down. Rob, looks like you want me to go over section 10.2. Were the exit ticket problems okay for that, or any particular one from the independent practice? Let me know. But we can definitely do that. So for 49, we know the square root of that is a 7. Square root of 2 doesn't simplify, but we know that the square root of x squared is an x. The square root of x is just root x, doesn't simplify. And we know that the square root of y squared is y. The only other component here is what is the square root of negative 1? Well, we're going to label that as I. Okay? Anytime you see that you need to evaluate the square root of negative 1, substitute I in for it, because we know that I squared is equal to negative 1. That's going to be the key definition that we saw for these types of problems. Exit ticket problems. All right, we can do that. Let me get through this section, and then we'll do a couple from 10.2. Now, all we did in this problem was we've added this extra step. Take the square root of negative 1. Now, I want to go through and make sure we're comfortable writing this problem. A lot of people, when they submitted the exit tickets, they had a mixed way of writing out the final solution. So I'm going to recommend that we write our solutions starting with the number, and then the variables that are outside of the radical, and then the I. Then we can write things inside the radical. The reason I do this is I'm really just replicating what the book does. Several publishers stick with this format. There's not really any particular reason for it. Like I had a student the other day say, couldn't I also write this, where we just move the I up front because it's all multiplication, what's the big deal? Yes, that's true. These are both equivalent. We just say let's have a system in place that we all use, so that way when we go about writing our answers, and of course if we have to add like radicals or like terms, we want to make sure we have a consistent way of writing them, just so it's a little more, I guess, visually appealing for us, easy for us to see visually what we need to do. Let's do one more problem from the exit ticket. This is one where we have an expression, a radical expression inside a larger expression, okay? And anytime we said that we come across these, we should really try to break down the radical first, okay? Try to simplify the radical and then substitute in what you get. So why don't we do that to the side here? We have the square root of negative 80, x to the 7. Oh gosh, what is the square root of negative 80? Well, first we can pull out the negative 1, and then 80, 16 and 5. Those are two factors of 80. And then the square root of x to the 7, I'm going to break up into x to the 6, and the square root of x to the 1st. Now, as we go through here, we can say the square root of negative 1 is I, the square root of 16 is 4, root 5 doesn't simplify, but the square root of x to the 6, hopefully we're getting quick with that to say it's x cubed, right? You just divide by 2, and then root x doesn't simplify. So our answer, if we're sticking in this format, should be 4 x cubed, then I, and root 5x. Again, if you don't stick in this format, like if you swap the I and the x cubed, that's fine. I'm not going to mark you off for that or anything. Let's just try to have a consistent method. All right, so with that, we can substitute it in 3 times. Instead of the square root of negative 80x to the 7, we have 4 x cubed I root 5x. And that is going to be all over 2x squared. Let's do our multiplication. That is a 12. And we have an x cubed. We have an I and a root 5x. And that's all going to be over 2x squared. Well, 12 divided by 2 is 6. X cubed divided by x squared is x. And then we have an I root 5x. Those don't simplify. Now, a student had asked me in previous classes about trying to simplify things with I. And the student really, after talking with them a little bit more and trying to clarify what they were asking, people seemed to think of I as being like a variable. Ahmed, you're asking, do we write anywhere that I equals square root negative I, or should we just assume? Oh, you can just assume. Like, that's actually defined. Like, mathematically, I is defined as the square root of negative 1. So you don't need to actually, in your work, state that. No. Like this symbol I, just like pi is a constant symbol, same thing with E or whatever, I is actually a defined symbol. So we can just assume everyone knows that. You don't have to go and redefine it. Good question. And with that, I want us to make sure that we realize here that I is not a variable. It really is just a symbol, okay? It's a unit. It's called the complex unit, in fact. And it's just a unit that has this property, okay? So it's not a variable where we can substitute things in for it. Like x here, that's a variable. My stylus is like dying on me, so apologies for the bad handwriting. X here is the variable. You can substitute values in for that. But I here, it's a standalone thing. It's not a variable. So don't try to substitute values into it. And also realize that it behaves a little differently than regular real numbers or variables do. And one of the things, we were going over a problem like this where we see how certain x's cancel out. And the student had asked me, well, Linford, what if we had something like I over I? Couldn't we just go and cancel those out? And I thought that was a really great question to think about, because the idea gets back to I really is it's a new unique concept for us. It's this complex unit where we can say it evaluates the square root of negative 1. So I'm going to hold off on answering this for right now. And instead, I'm going to let people try to think about this a little more. I know that this is today's Wednesday live stream session. I'm going to check back in on Monday. Maybe I'll post a little explanation over the weekend or something. But I'd like you to try to think about this problem. What would I divided by I be? Could you cancel things out, or would it become something else? So let's take a thought on that. I'll give you till Monday to think about it. All right, let's try a couple practice problems from the homework. I had a student email me if we could go over these problems, and then I'll get into, Rob, your 10.2 problems, okay? Now, for this problem, this should remind us, similar to some of the problems we did, I think from 10.1 and 10.3, where we have an expression inside the radical. Now, there's a couple ways of thinking about this. Now that you have a deep understanding of radical expressions, you might say that we can take the square root of the numerator and we can take the square root of the denominator. And we can try to break this down, simplify it. It looks like, though, we're going to end up with a root in the denominator that we're going to have to rationalize and do quite a bit of work with that. But there's another technique that we could do. Besides just going and taking the root of the top and the root of the bottom, we could actually simplify the interior first. So negative 4 over 100 is negative 1 over 25. And h over h to the fifth is h to the fourth. So we've gone through and we've simplified this down. Now we can say to ourselves, can we go and take the root of the top and the bottom? So let's take the square root of negative 1 on the top, the square root of 25 h to the fourth on the bottom. Let's see, the square root of negative 1 is I, and the square root of 25 is 5, and the square root of h to the fourth is h squared. It's almost as if I planned it that way. So, obviously, in this particular problem, it made sense for us to try to simplify the interior first before we took the square root. Will that always work? When you simplify the interior, will you end up with a nice, perfect square denominator? No. It only worked because Mr. Linford planned it that way. In other cases, what you would have to do is you would have to square root the top, and you would have to square root the bottom, and you would have to go through and then try to rationalize the denominator. If anyone wants me to go over that, just let me know and I can review that, but I won't ask you anything in particular like that on any of the homework problems. Really, I'm just looking for you to try to simplify the interior first. And then the last one the student asked me about was to go over problem 8 from the independent practice. If there's any other problems you want me to go over from independent or advanced practice, let me know in the live chat. And if there's any questions that you're having, I know we're only about 13 minutes in, but I feel like I might be moving a little fast for some people. So if you need me to slow down or explain anything more, just let me know. All right, let's go ahead and we're going to treat this problem like we did with the practice problems from the exit ticket the other day. So since we have a radical expression inside of a larger expression, we're going to simplify this down first. We have the square root of negative 162, x to the 9th, y to the 4th. All right, let's break down the square root of 162. Oh gosh, I don't even know what the factors of that would be, so let me grab my calculator and start testing. Oh, look, 2 and 81. There's a perfect square. So I'm just going to stop there. I don't need to do the whole prime factorization. Let's split this radical up into the square root of negative 1, the square root of 162. X to the 9th we can split up in x to the 8th and x to the 1st, and then the square root of y to the 4th. So before I start simplifying anything, I'll just split up 162 again. By the way, these live streams, I make sure to post them right after we're done with them. So if anyone misses anything or needs to go back over any problems, just let me know. You can check on my YouTube page. It'll be posted right after this. So the square root of negative 1 is I. Square root of 81 is 9. Root 2 doesn't break down. But the square root of x to the 8th breaks down into x to the 4th. Root x doesn't break down, but root y to the 4th will break down into y squared. Hopefully you're recognizing that when we need to break down roots, we really just divide the exponent by the index. Okay, this is kind of messy, but let's try to write it in our form. We have the number first, followed by the variables, and then we need to write the I, and then we can write what's in the root, okay? Again, is it vital to write it in this way? No, but a lot of times when students don't have a consistent method for writing them, they tend to mix stuff up. Okay, let me switch colors here. And I'm going to go back into the original problem, x squared y, and we're going to multiply this by 9, x to the 4th, y squared I, root 2x. And we're going to divide all of this by 18, okay? You know me, I'm a big fan of color coding, and I would recommend that all students, do some type of color coding or have some way of organizing their work, especially before you go and take the Unit 5 exam. Have some way of organizing so when you break these components down, it's not all one big mess. So let's see, x squared and x to the 4th is x to the 6th, y and y squared is y to the 3rd. We still have I and root 2x, and that's over 18. Well, we can simplify one step further. 9 and 18 can simplify. So we have x to the 6 on the top. We have a y cubed, an I, a root 2x, and on the bottom, we have a 2. Hopefully this part makes sense to everybody. Really nothing new here. The only new concept, I guess, is that the square root of -1 is this I term. So all we have to do is sub that in for our answer. One thing I was seeing that people were doing the other day, they were thinking that if they had the square root of something like -b squared, they were saying that's -b. So keep in mind, negative roots don't mean that you have a negative number on the outside. That's not true at all. They mean that you have an I value. You have a complex unit. If you have a negative root, you are no longer dealing in real numbers. You have to be dealing in complex numbers. Let's take a minute and let's jump back to 10.2. Rob, you asked about the exit ticket problems. Right now, if there's none in particular, we could do both of them. Let's start with the first one. One from 10.2. For the exit ticket, it is 3x to the 3/4 power times 2x to the 2/3 power. All right, so first up, we obviously can multiply the 3 and the 2 together to get 6. Then we have to multiply the x to the 3/4 and the x to the 2/3. Well, how do we multiply like bases? Hopefully you're recognizing that when we multiply like bases, we have to add the exponents. So this is going to be 6, x to the 3/4 plus 2/3. So you can go and you can make a common denominator. You can add 3/4 and 2/3 together. I'm just going to cheat. I'm putting it into my calculator really quick and converting it to a fraction. It is x to the 17/12. Now, here's where a lot of students stopped on the exit ticket. You actually need to go a step further and convert this into a radical, okay? So our answer should be 6 times the 12th root of x to the 17. Remember, when you have a fraction exponent, the denominator of the fraction is the root. This tells you what root we're taking. And the numerator just tells you what's the exponent on the value. Here's something I was seeing quite a lot of. I was seeing quite a bit of this where students were taking the root of everything that was written down. We don't want to do that because remember, exponents only affect what they're immediately touching. So the exponent is not affecting all of 6x, it's just affecting x. That's the only value that we need to worry about here, okay? And a lot of times students stopped here. I met with a couple students the other day and I said, wait a minute, take a closer look. And they thought about it and then they realized, oh wait, we can keep breaking this down, can't we? So they decided, all right, instead of writing the 12th root of x to the 17, let's write x to the 12, and then the 12th root of x to the 5th. Because they said we need a group of 12. Well, we have 17, so we can do that. So the 12th root of x to the 12 is x. And then the 12th root of x to the 5th, well, that doesn't simplify. But that should be our final answer. We have 6x times the 12th root of x to the 5th. So that was problem 1 for the exit ticket. There are a couple ways, few different ways of going about doing this, especially starting right here. I covered those Monday actually, in the live stream, both the morning and the afternoon section. So if you'd like, go back and check out Monday's live streams. I do them a couple different ways. So, if this way isn't making sense, try to look at some of those older videos and see if they help out at all. Let's go ahead and let's do problem 2. Rob, let me know if you have any questions on these, okay? But problem 2 here, let me jump a couple pages. All right, section 10.2. Let's do number 2 from the exit ticket. Let's see, it's a 16, x to the 5th, y to the 3/4, and all of this is to the 4th power, or the 1/4 power. Now, hopefully you're realizing that in the last problem, everything that we did was really governed by the rules of exponents. And that's basically what we're going to do right here as well. We're using the rules of exponents, except this time, the exponents are fractions. No big deal. It should all behave the same way. It's just when we get to simplifying, we need to make sure we're comfortable turning them back into radicals. So, one of the things that we can do, you could go ahead and just say that you want to take the 4th root of everything, right? You want to take the 4th root of this whole quantity because the 1/4 power is touching all of these terms. But that kind of doesn't always help you simplify because what does it mean to have the 4th root of y to the 3/4? So this method, it was okay, but we generally didn't do this when we had exponents on the outside. What we actually would do is we said, think back to the power rule, or the power of a product rule. And this is where we distributed, and I'm saying that in air quotes here, we distributed the 1/4 power through, or I should say we applied the exponent through. So let's go ahead and let's do that. Again, I'm just using the rules that we used earlier in class and seeing how they help us out. All right, obviously, we can evaluate 16 to the 1/4, right? The 16 to the 1/4 is basically saying, what is the 4th root of 16? Well, that's just 2. So we got a value for that. Okay, cool. But now we have x to the 5/4 power. Remember, when you take an exponential to an exponent, you have to multiply the exponents together. So we get x to the 5/4, and we have y to the 3/16 power, okay? A lot of times students got here, but they forgot, oh wait, we got to convert these to radicals. So what they said was we have 2, and we have the 4th root of x to the 5th, and we have the 16th root of y to the 3rd. And here is where students then stopped. Now, one of the things I wanted to point out was, well, I guess you could stop there, but we really want to try to combine these fractions into one thing, okay? We wanted to have one radical expression as opposed to 2. So, what do we need to make one radical expression? What do we need to get these radicands under the same radical sign? Well, think back to the beginning of the previous series of lessons. I think it was 10.1. Remember, we had this process that if you're taking the root of two things multiplied together, we said you could separate it and take the root of each thing individually and multiply them. So this is how we typically would go about doing this. We'd split it up. It also works in reverse. As long as you have the same index, you're taking the same root, you can remultiply these things together to fit under one radical. So what's the challenge here? Well, the challenge for us is that they're different indices. One's 4 and one's 16. So we got to do something to change the indices so that they become the same thing, so we can multiply them. I'm going to suggest we go back one step. I'm going to suggest we start by looking right here. Notice, again, that the denominator controls what the index is. Okay? That controls the root. So I want these denominators to essentially be the same thing. I want the 4 and the 16 to be the same value. Okay, here's a really, really tricky question. What could you do to these fractions, 5/4 and or 3/16? What could you do to the fractions to make them have the same denominator? I'll give you a minute to think about it. All right, time's up. Hopefully, you're saying, multiply the top and the bottom by the same thing. Multiply the top and the bottom here by 4/4. And let's see, what do we get? We should end up with, well, we still have that 2, x to the 20/16, and y to the 3/16. Is 20/16 the same thing as 5/4? Yeah, it is. So really, this isn't that complicated. All we're doing is just changing the fraction, making it less simplified. Now, when we first learned about this, it was a little bit more complicated because we didn't have this understanding of rational exponents. We said you got to keep the exponent and the index in the same proportion. Here's why. It's because they're really just fractions. So if you need to get them to be the same index or the same denominator, just make a common denominator. It's easy as that. Now, they're both under the same root. We have the 16th root of x to the 20 and the 16th root of y cubed. So we can say that's 2 and the 16th root of x to the 20 y cubed. And there we go. We've paired them together. And this, after talking with students, is to where students really got their work to. And they said, yep, a lot of students said, here we go. We finished a little bit lengthy of a problem, but not too bad. All we did was we use rules of exponents, made a common denominator to group things together, and we're done. And then I said, wait one more second. And this is where students start to groan. They're like, oh my gosh, what else do we have to do? Well, hopefully you're seeing there's an x to the 20th inside of a 16th root. Hopefully you're noticing if the exponent is larger than the index, you can simplify it. Okay? So we do need to keep simplifying this. We got everything into one root. Let's keep breaking it down. Let's take the 16th root of x to the 16th, the 16th root of x to the 4th, and the 16th root of y cubed. Now, that's 2. The 16th root of x to the 16 is just 1x. Did I say that right? The 16th root of x to the 16th, yeah, that's just 1x. And then we have the 16th root of x to the 4th, y cubed. There, that is our final answer. I promise. That's all that we'll need to do for here. Okay? Please make sure when you go and we know this about when we multiply radical expressions together. We should also know this about when we start messing with their exponents and taking rational exponents. Oftentimes, when we multiply things together or group them together, we will end up with a situation where the radicand can now be simplified down. Okay? Always look out for that. I'd say it happens about 65 to 70% of the time in homework problems and on tests. These are things you got to look out for. Okay? Rob, hope this answered your question. If not, let me know. What I would also suggest is taking a look at the live stream again from Monday, the morning and the afternoon live streams, the AM and the PM one, because in both of those, I did go over this problem, but I did it in a couple different ways. So check it out, see which method works for you, and if you have any questions on them, just let me know. Okay? We've only been 30 minutes into this, and I feel like I'm covering quite a lot. Are there any questions that people have? Any problems in particular you'd like me to go over or review? Oh, Rob, yes. Yeah, Edge Elastic is actually using an incorrect answer key. I originally made one exit ticket, and then there was an error to it, so I changed it around. But for some reason, it's not taking the new answer. So I'm just going through one at a time. Hopefully that made sense. Don't worry if Edge Elastic's marking your problems wrong. I'm actually going back through them and manually adjusting all of the grades. Not seeing any other questions that people have or topics they'd like me to go over. So I think I'd just like to cover just a couple of the problems that we're going over today. These are two types of problems similar to what you'll see in the exit ticket. And then I think we'll finish up here. In today's discussion, we're going over how to actually perform algebra on complex numbers. So we've learned about complex numbers, what they are, and anytime we learn about new mathematical objects, right, whether they're real numbers or regular or complex numbers, we want to make sure that we can perform algebra on them. What happens when we start manipulating them and using them in arithmetic? So, for example, what might happen under addition, subtraction, and multiplication? And tomorrow we'll learn about what happens with division. So first up, let's take two complex numbers and let's add them together, okay? The first thing that we have to try to do is understand, well, how do we go about adding complex numbers? Remember that when you have complex numbers, they're of the form a plus bi. The a part here is the real component, and the bi is the complex component. So when you go and add complex numbers together, we're actually going to add the real components, and we're going to add the complex components. This should be identical to when you would work with polynomials. You would just add the like terms. So we're going to add the 5 and the 2, so that makes us 7. We can add the 3i and the negative 7i to be negative 4i. That is going to be our answer. There we just added two complex numbers together. And doing that, we added the real parts, and then we added the complex parts. And hopefully that makes sense, because if you're just trying to add the regular real part and then the regular complex part, they don't really combine, do they? That's why we have to write things like this, because they don't add together. They're not really like terms. Similarly, when it comes to multiplication, we can also think of this as if we were dealing with polynomials. We have 4 plus 3x and 2 minus 5x. What did we do in this case? Well, we just distributed. We would distribute each term through individually to the other terms. And you know my preferred method of distribution is the box method. So we can do that again here with the complex numbers. I'm going to take 4 and 3i, and then I'm also going to take the 2 and the negative 5i, and let's distribute each thing through individually. So 4 times 2 is 8. 4 times negative 5i is negative 20i. 2 times 3i is 6i. And let's see, negative 5i times 3i, that's negative 15i squared. So let's try to write our answer out. We end up with an 8. We have these like terms here. So negative 20i and 6i is negative 14i. And then we have minus 15i squared. Notice, though, that this is not a complex number, right? what's this I squared business? Okay, that was not how we wrote complex numbers. So how do we go about enforcing this to be a complex number? We actually have to keep simplifying. Remember, I squared, how do we define it? I squared is just -1. So really we have 8 minus 14i minus 15 times -1. Well, -15 times -1 is just positive 15. -15 and -1, yeah, that's just positive 15. So 8 and positive 15, that should make 23. And then we have the -14i. There, that fits the form of a complex number. And that's the number that we want, 23 minus 14i. Anytime you multiply complex numbers together, you're going to end up with some term that has I squared to it. Please just remember that I squared is equal to -1. So you're going to have to substitute that in for the I squared. When you do that, these will become like terms. Oop, looks like I lost my screen mirroring for a second. So just go ahead and recognize that when you substitute those values in is when you're going to go about combining those like terms. Well, it looks like my iPad kicked out from the screen mirroring for right now, but that was pretty much it for all the content I had to go over, or I thought about going over. If you have any questions, let me know. Otherwise, we can end the live stream a little early. The big thing that I want people to understand from this is to make sure, one, that they're feeling comfortable working with simplifying radicals still, this time by adding in negatives, okay? When you have a negative radicand, remember, your answer is no longer a real number. It's going to be complex, so you have to deal with the I stuff. Additionally, being comfortable with the algebra of complex numbers, okay? As you work through this section today, you're really going to realize that you know how to do all of this stuff already. It's pretty straightforward and simple. We're just redefining it, okay? With that said, I think I'm going to end this live stream for right now. I'll get the video posted up as soon as we're done here so you can look back if you have any questions. Otherwise, feel free to send me an email. And until next time, take care.